What if I told you that you can decide the past right now? It sounds like science fiction, but this idea came from one of the strangest experiments ever conducted in modern physics. What you're about to see isn't some crazy internet theory. It's a real experiment, repeated and verified, that challenges everything we know about time, causality, and reality. Get ready to question what is real, because what's coming may have already happened. In this video, you'll understand how quantum mechanics has shaken our understanding of cause and effect, and what that reveals about the very nature of the universe. Quantum mechanics is our best theory to describe the microscopic world, where atoms, electrons, and quantum fields act to form everything we experience as reality. Despite its absolute success in describing this tiny universe, quantum mechanics has a unique feature. It doesn't always tell stories that we can easily understand. To make sense of the strange quantum world, we often need to create interpretations that are mathematically unnecessary. The math works, but without these extra explanations, the theory is not easily comprehensible. In the classical world, everything around us has a beginning, middle, and end. A ball flying toward the goal was always kicked by someone and will always stop, whether at the goalie, the net, or even in the stands. Airplanes fly thanks to complex forces, but these forces tell a coherent and understandable story. Even Einstein's relativity, with its 4 dimensions and curved spacetime, allows us to create clear narratives explaining events like black holes and gravitational waves. These stories help us deeply understand physics and the universe, going beyond just the formal math. But quantum mechanics doesn't work like that. Today I am going to present an experiment that convinced some of history's greatest physicists that the future can, in some way, determine the past. A concept called retrocausality. Let's start with the classic double-slit experiment, one of the most important in quantum mechanics. In it, something is thrown against a wall with 2 slits. And behind that wall, there's a screen where the mark left reveals information about the nature of what was thrown. In the classical world, particles have well-defined positions, like soccer balls. If you throw particles through the 2 slits, they pass through one or the other and leave 2 stripes on the screen, one behind each slit. Waves, on the other hand, have no fixed position. They spread out and pass through both slits simultaneously, creating an interference pattern on the screen. Alternating stripes, marking regions where the waves add up or cancel out. This pattern reveals that something passed through both slits at the same time, behavior impossible for classical particles. In the microscopic world, electrons and photons, which make up light, can behave like particles or waves depending on how we set up the experiment. Shooting one electron at a time, we can see either a 2-stripe pattern typical of particles or an interference pattern typical of waves. What determines this is whether or not we measure the electron's path. Placing a detector at the slits reveals which slit it passed through, and the interference pattern disappears. The electron behaves like a particle. If we don't measure, it behaves like a wave. This behavior is called wave-particle duality, a fundamental feature of quantum mechanics. Quantum nature seems to be formed by 2 opposite things coexisting at the same time, but we can observe only one side at a time, like a coin that can be heads or tails, but never both simultaneously. Complementarity is the deepest concept of quantum mechanics. Learning a particle's precise position destroys information about its velocity, and vice versa. This applies to other properties too, like the orientation of the magnetic field. Everything in quantum mechanics is complementary. Now, imagine an even stranger experiment: the delayed choice double-slit. Here we put detectors to know which slit the electron passed through. But we decide whether to use this information only after the electron has already passed the slits, or even after it has hit the screen. The surprise is that the final pattern on the screen depends on this future decision. If we decide to read the path information, the pattern is particle-like. If we decide to erase this information, the interference pattern reappears. In other words, the electron's behavior seems to be decided by something that only happens in the future. This challenges our intuition of linear time and cause-effect. How can a decision made in the future influence the past? For some physicists, this is so strange that the idea of retrocausality became a serious possibility. But don't worry, this doesn't mean we can send messages to the past or create time paradoxes. Quantum mechanics has a fundamental limit. quantum information is encoded in complementary states. Measuring one property destroys information about the other, preventing the transmission of retroactive messages. The key is quantum entanglement, where particles correlate so that their properties are interdependent regardless of distance. In this experiment, the quantum signal carrying the electron's path information is entangled with the electron itself. What happens to the signal determines the electron's behavior, and vice versa, in perfect symmetry. This symmetry allows interpreting the experiment both as the future influencing the past and the past influencing the future. And both are mathematically correct. The quantum universe doesn't need to follow our classical logic of cause and effect. What the delayed choice double-slit experiment reveals is that the quantum world, dose and T, have to tell stories we can understand. The math works. The results are precise. But the interpretation is a challenge for our minds, limited by classical physics. This discovery opens doors to new reflections on the nature of time, reality, and consciousness itself. Could time not be a straight line, but something more flexible and interconnected? Could our choices now affect not just the future, but also the past? These questions still have no definitive answers, but already show us that reality is far stranger and more fascinating than we imagined. Quantum physics invites us to accept a vision of the universe where observer and observed are intertwined, where truth depends on the question asked, and where time might be a more mysterious dimension than we think. If you enjoy exploring these mysteries and want to keep discovering the secrets of the universe, leave a like, subscribe to the channel, and hit the notification bell so you don't miss the next videos. And of course, leave your thoughts in the comments. Do you think the future can influence the past? Or do you believe we still have much to learn about time and reality? Thanks for watching, and see you on the next journey through the incredible world of quantum physics.